This is AQA A-Level Chemistry. It's the energetics topic and we are now on part 4. We've previously looked at Q is MC delta T and we've also looked at definitions of some key enthalpy changes. In this one, we're going to start to use those enthalpy changes and we're going to start to look at Hess cycles. So as always, I'm going to recommend that you pause as you go, try the activities and then review them. And you then get a chance to go and ask for help, go and speak to your teachers if there are things that are still not quite clicking into place. So in terms of Hess's law, we need to know what it is and we need, crucially, to be able to use it. Before we actually get on to that, we've got the law here. The enthalpy change for a given chemical reaction is the same whichever route is taken from reactants to products. So we're going to build that into calculations later so we can actually see precisely what that means. But to begin with, this is a good chance for you to just refresh your mind on enthalpy of formation and enthalpy of combustion and have a think about whether any of these equations do represent an enthalpy of combustion or an enthalpy of formation. If they don't, we have a third way to consider, and we would call it an enthalpy of reaction, which is a generic term. Now in year 13, we had a lot more definitions, but for now, they're the only 3 that we need to consider. So have a think about them. Have a think about the standard enthalpy of formation for any element in its standard state and why that's the case. And then when you're ready, unpause and we'll review. So if we take a look at the first equation here, we're making 1 mole of C3H8. We're making it from its elements. They're in their standard states at standard temperature and pressure. So that one is an enthalpy of formation. On the next one, you can see that we're starting with 1 mole of propane. We're reacting it in a ready supply of oxygen, and we can see that all products and reactants are in their standard states at standard temperature and pressure. So that one is enthalpy of combustion. And just to point out, as I mentioned on the previous video, this liquid on the H2O is absolutely vital. We do have reactants and products in their standard state under standard conditions. On the next one, what type of enthalpy change is this? Well, we've got ethene and hydrogen, and we're making ethane. So it is hydrogenation of an alkene, but what type of enthalpy change is it? Well, in this case, it's not formation because we're not starting with elements. It's not combustion because we're not reacting with oxygen. We're not combusting. So that one is an enthalpy of reaction. And what about this final one? We've got ethane reacting with oxygen to make carbon dioxide and water. All reactants and products are in their standard state. So the initial thought might be that this is enthalpy of combustion. But actually, enthalpy of combustion is the combustion of 1 mole of a substance, and we're combusting 2 moles of ethane. So this is an enthalpy of reaction. But alternatively, you could say that this is twice the enthalpy of combustion of ethane, because it would be twice the value for 1 mole being combusted. And then we've got this question about the standard enthalpy of formation for any element. Well, if you think about it, standard enthalpy of formation is the enthalpy change when 1 mole of something is formed from its elements in their standard states. So if I'm making an element in its standard state, there is no change. So it's 0 kilojoules per mole. And you could answer why in a very long-winded way, but essentially it is because it is. It is by definition. And that's what you'd be looking to put down as your explanation. So let's do a little bit more reinforcement and do some enthalpy of combustion equations. We've seen these back on video 2. Pause and see how you do. So in the first instance, I've got carbon. I'm reacting it with oxygen and I'm making carbon dioxide. It's balanced. I'm combusting 1 mole of carbon. So I'm happy that I've got all of it, but I still don't have all of the detail that's needed. Because the definition talks about states, it has to include the state symbols. Carbon is solid, oxygen gaseous, carbon dioxide is gaseous. And that is true under standard conditions, 100 kilopascals atmospheric pressure and 298 K. On the next one, I am combusting hydrogen. So I react hydrogen with oxygen, remembering they're both diatomic, and I'm making water. Now you might be tempted to multiply these up and have 2H2 plus O2 goes to 2H2O, but that no longer satisfies the criteria for enthalpy of combustion. Instead, we need half O2. And at that point, I put my state symbols in, and the one to watch out for, as I've already mentioned, the water is a liquid because it cools back down to that. That's what it would be once it's returned to standard conditions. The next one is methanol. So I react my methanol and I've got 1C, so 1 CO2, but I have got 2 H2O, which means that I need 1.5 O2. Be really, really careful when balancing combustion of alcohol questions. There's already an oxygen present. So I might have 4 oxygens on that side, but I only need 3 extra to balance it. And then the state symbols, once again, I put those in and we're done. So let's take a look at why we might need to use Hess's law and Hess cycles. Take a look at the equation that has been given here. You've got some reasons why we might not be able to do something practically. The activation energy might be far too high. The reaction might be far too slow. It might be multiple reactions take place. Which of those do you think is the case when we look at the equation in bold here? 3 carbons plus 4 H2 goes to C3H8. Why can we not measure that directly? Okay, so if we think about this, carbon reacting with hydrogen makes hydrocarbons, doesn't necessarily make C3H8. It could make a combination of hydrocarbons. So we would not be able to say with absolute certainty that my product was C3H8. That's why we need to apply Hess's law. And in the remainder of this video, we're going to introduce the key principles of Hess's law that we're then going to go on to use in calculations. So I wanted to take a look at what we have here. We've got A reacts to make B, but alternatively, we could convert A to C and then C to B. So if we take a look at that, we can see there are 2 different routes. And what I'm going to do is start to build those 2 routes in. We've been given information about the value of A to C and C to B, so let's put those on. A to C is plus 10, C to B is minus 14, so we need to find out what A to B would be. And what we get is the sum total is the same. Plus 10 and minus 14 is equal to minus 4. So because Hess's law tells us that the overall energy change is the same whichever route is taken, we can be confident that that is minus 4. Let's have a go at the next one. Now what I'm hoping you've done here is paid close attention to the arrows, because these aren't the same as the one we had previously. On here we've got A going to B, but we have A going to C and B going to C. Let's put the figures in. We've got X that we want to work out. We've got our plus 47 for A to C. We've got our minus 714 for B to C. And now we need to find our 2 routes. And what's clear when you follow the arrows is that both routes start at A and both routes finish at C. So at that point, I can start to put my figures into an expression. I can see that X take away 714 is equal to plus 47. Let's rearrange that to make X the subject, and we have an X value here of 761 kilojoules per mole. So let's try another one. Again, on this one, the arrows are moving in different directions, so we've got to be careful in identifying what our 2 routes are. But I put my figures in. I've got my plus 1368, I've got my minus 638, and I've got my X. My 2 routes start at C and end at B, because at C I have 2 arrows leaving, at B I have 2 arrows incoming. That allows me to now put those figures in, and I have 1368 plus X is equal to negative 638. I rearrange that, I make X the subject, and that allows me to calculate that X is negative 2006. And that gives us the basic introduction to Hess cycles. As we move forward, we're going to start to apply these to the more complicated exam style questions that you are likely to see. Thank you for listening. Goodbye.